In this video, I'm going to talk about the 4 factors that determine the magnitude of the elastic or non-permanent change in the length of a straight bar. So envision, this is a 1D problem. Envision we have a straight bar which has uniform cross-sectional area, and it could be either rectangular or a tube or any kind of length of anything, and we're going to just pull on it just in the axial direction with a force. We're either pushing or pulling on it, and the length of this element, if I pull on it, it's going to get longer, and if I push on it, it's going to get shorter. And so question is, what are the 4 factors that determine what's the magnitude of that change in length, either pulling getting longer or pushing getting shorter? So, and this is a non-permanent, so we're just, so if I pull on it and I let go, and the force goes back to 0, it'll go back to its original length. There's no permanent change in it. So these 4 factors, pause the video right now, think about it, write the equation, and then we'll talk about it. The first factor that affects the elastic change in length of the bar is the magnitude of the force. If I double the force, I double the change of that elastic deflection. So there's a proportional relationship between the change in the length and the force. The second factor is the length of the bar. If I double the length of the bar relative to this one, I'm going to have twice the elastic deflection. So once again, a proportional relationship between the change in length and the length. The third factor is the cross-sectional area. So perpendicular to this force, whatever this area is, if it's a rectangle, it'll be then the width times the height. If it's a tube, it's this area that sees that. So whatever geometry I have at the end, or through each cross-sectional cut, that area. So if I have something that has a big area, then I'll have less deflection. If there's smaller cross-sectional area, then I'll have more deflection. So there's an inverse relationship between the change in the length and the area. The more cross-sectional area, the less change in length. The fourth element is the material. And the property that we're interested in is called Young's elastic modulus. So if I have identical bars, one made out of something, let's say steel, which has a high elastic modulus, another material, for example rubber, which has a very low elastic modulus, the rubber one will have a greater elastic change in length. So this Young's elastic modulus, which is most commonly shown as E, but in your text is Y, so Y for Young's or E for elastic modulus, that's also inversely related to the change in length. So here is the ultimate equation for this change in length, and these 4 factors, and this is a good thing, just you can think about these 4 factors, but this is a good starting point to understand that relationship. And then again, it's either Young's elastic modulus is either Y or common than E, and the units of this, well, force is going to be units of force, for example, Newton, lengths, area is going to be length squared, for example, meter squared. The units of this, Y, to make this all work out is a unit of pressure. It's a force over an area. This is a good way to remember this. So change in L is force, length, and then divided by the cross-sectional area in Young's elastic modulus. With some simple algebra, this equation can be rewritten, bringing the y up here and taking the delta L down here, the change in length, to come up with this formula. And then if I just rearrange this, put this in this term in the numerator, flip this over, put it in the denominator, I'll end up with this equation, which is the exact same as this, just in a different form. And it's saying the Young's elastic modulus is the stress. So I put stress on a part, I put so much force on it over area, that's stress, has units of pressure, and there's a resulting strain which comes from it. So the strain is the change in length over its length. So that's a dimensionless one. So Young's modulus defines when I put a stress on something, I put a force on over an area, the higher the force, less area, the more stress I put on it. There's a strain that comes up, and this relates those two. when I have the length of the bar defined, the cross-sectional area of the bar defined, and the material of the bar defined, the stiffness relates the change in force to the change in length. So if I draw a graph right here where the y-axis is force, I'll call positive a value of pull, a negative value would be push, and 0 would be no force at all applied, and the x-axis would be the length. And we're going to take some data on this. We're going to start with a bar at some length, then I'll put a force on it, and it's getting longer and longer. Take some data, and if it's elastic and linear, the more I pull on it, the longer it'll get. If I push on the shorter it'll get. When there's no force applied on it, the length of this undeformed bar is sometimes called the relaxed length or the unloaded length or the free length. It has many names. But I'll get this data showing it gets longer when I pull on it, it gets shorter when I push on it, and I'll assume it's elastic, non-permanent, and it's linear. Slope then relates the change, so slope is the derivative. In starting courses, you're pretty much always going to assume this is linear, but truly it's the derivative, so the tangent point, whatever load I'm in, if it's linear elastic, then it'll be a linear relationship, but it's the derivative of the change in the force divided by the change in length. So it relates this characteristic, so with everything else being fixed for this case. So it's the change in force or the change in length, which if it's linear elastic, then I'll have the delta force over delta length. If I say my force minimum is 0, then it's just the magnitude of the force. So that's the magnitude of the force divided by the change in the length. Okay, so this is the magnitude. So the change in length is the change in length from 0 force to whatever force I have applied. Okay, that's defined as the stiffness, and that just comes from rearranging the equations in this term. So I have force over change in the length. That's what my stiffness, elastic stiffness is. So if I just take these terms and rearrange it, I can rearrange that to become it's the cross-sectional area times the Young's modulus divided by length. And this has units. So stiffness is for a force how much deflection I get. So it's a force over deflection. So this be the definition of elastic modulus, and you can see how stress, when I apply a stress on something I get a strain, and how stiffness, they all come and relate back down to this basic equation. So you can you remember it in some forms. I think it's kind of easiest to just remember that and then remember these definitions following it.